Okay, so let's go and take a look at our homework and questions we have on it. I want to go ahead and address a couple of things from what people have asked me so far. So if you take a look at the bottom proof on the front side here, number 5, there is a different way that you can go about doing this. So I took the approach of saying these lines were parallel and then using corresponding angles. You could have, instead of going down the parallel line approach, so I'm going to scribble out this guy. I still need to state that these angles are right angles by definition of perpendicular lines, and I still need to state that that then means that they're congruent because all right angles are congruent. That's your right angle congruence there. So I still need to have steps 3. Well, and this one steps 3 and 4. But what you could do differently instead of using your parallel lines is you could have said angle D is congruent to angle D, and that would be by reflexive property. And then we would have by angle that way. So that would have gotten you 5 steps instead of 6. So again, you could go ahead and use reflexive property, but you still have to state, they told us perpendicular, so we have to translate perpendicular definition tells us that means they're right angles. And then right angle congruence there tells us the right angles are congruent. So again, if I have angle-angle similarity, I'm looking back in your proof, I should see 2 statements where angles are congruent. And then on the back side, number 8 here. So you'll notice I've drawn in here parallel lines. They did not give that to us, but we do know that they're parallel because if these are congruent here, that means D is the midpoint on that side. And again over here, if NP and PN are congruent, then that means P is the midpoint. What do we call that segment when we connect the midpoints in a triangle? Mid-segment, good. The segment that connects the midpoints, mid-segment. And we have the triangle mid-segment theorem says that our mid-segment is parallel to the third side, as well as it's half the length of the third side. So that's how I knew that those were parallel. And then we could say, using our course, so we've got reflexive, and then using corresponding angles, we could say angle-angle similarity, or even just straight up corresponding angles. Now you could have also used side-angle-side similarity. And that's because if I compare this whole thing to just my little triangle, because these are congruent, it's like your ratio would be 2 to 1. And likewise over here, 2 to 1. So reflexive property, with that, could use side-angle-side. So there are a couple options for that. Okay. Do we have any questions on the front side you'd like for me to go over? Right there. And then, again, you're supposed to skip number 12. I apologize, it looks like Kip or up on yours. But do we have any questions on the back side? Yes. Are we going to learn something here? Oh, we're learning new stuff today. Yeah, lots of good stuff. Still dealing with similar triangles and proportions, but so we'll be doing practice with proportions. Good? Okay. You'll notice that a lot of times our proofs for similar triangles, if they're asking us to prove that triangles are similar, a lot of times it's using angle-angle similarity postulate. So just be on the lookout for that. So again, look out for reflexive property. If they give us parallel lines, look to see if there's corresponding angles that are congruent or alternate interior angles that are congruent. Perhaps even alternate exterior angles that are congruent. And then vertical angle theorem can come into play as well. But a lot of times our proofs use angle-angle similarity postulate. Okay. Also, with congruent triangles, we had CP-CTC, which basically said, once I know triangles are congruent, then I can say the pieces are congruent. Once I know triangles are similar, I can say either the angles are congruent or the sides are proportional. That's just our definition of similar triangles. But so kind of that same concept though. Once I have the triangles are similar, then I could say either those corresponding angles are congruent or corresponding sides are proportional. But again, usually our proofs are asking us to prove that triangles are similar, and we usually use angle-angle similarity. I think we did on each of those as well. Okay, we're good with that? Okay, we'll go and transition to our note. Okay, so if you take a look at today's notes, I personally like these ones because there's a theorem called the side splitter theorem. I think it's one of the cooler names in the book. But what we have today is we're going to learn about when we have this specific type of example. So when we have a triangle with that parallel line drawn through. This is not necessarily our mid-segment. They might give us our mid-segment, but not necessarily. So I don't have that C, B, and B, A are congruent. It's just this is parallel line somewhere through my triangle. Now we dealt with this type of problem last class. And I'll show you the problem we did. So we did this here, and we said how when we solve this type of triangle, you've got to be careful because I want to draw the triangles separately. I've got my small triangle. Oops. I've got my small triangle, which is 6 and x minus 1. And I've got my bigger triangle, which is 2x plus 4. And then what is this entire side?
6.
X plus 6. So we said you've got to be careful because x minus 1 and 2x plus 4, that's the entire side length of the triangle. So I can't compare that with just the pieces. It has to be compared with the entire side length. So I would say x minus 1 compared to 2x plus 4 is the same as 6 compared to x plus 6. Not 6 to x, but 6 to x plus 6. And so we had to consider the small triangle compared to the big triangle, and with that, we had to make sure we're talking about the entire length here and not just that piece of x. So what we're learning today is when we have these parallel lines, so these are theorems that deal with our parallel lines within triangles. And so what we're learning today is our side splitter theorem, which tells us another way that we can go about solving this without having to use small triangle compared to big. Now, if you're not certain, always go back to small triangle compared to big, draw them separately, and compare it that way. But what we're learning today is what can we do with those pieces when those pieces are given to us. So you'll notice these first two, it's just the original side splitter and the converse. And then these afterwards are called corollaries, which again is pretty much like a follow-up thought. So these stem from our side splitter. So corollary is just, it's kind of like a sub-bullet point, if you would. There's kind of a follow-through thought. Okay, I know side splitter. Well, because of side splitter, I can now say this as well. So you'll notice these are similar in that we have parallel lines, but we don't necessarily have a triangle. But of course, I could draw out these lines, and they will intersect, and we'd have a big triangle there. So these are all very similar. It pretty much comes from when we have parallel lines, and we're talking about pieces here. What can we do with those pieces? Now, on the back side, we've already talked about this. This is our triangle mid-segment theorem, so just recapping that, which, again, deals with parallel lines. And then, finally, something different, completely different than what we've done. This is our angle bisector theorem here when we're doing it within a triangle. And again, it's talking about what can we do with these pieces. The angle bisects, or this angle bisector connects to the line opposite. What do we know about those pieces in relationship to the sides? So this is what we're going to be doing today. And again, you also have in front of you this classwork, and we'll use these as examples. But this is kind of our focus here is when we have parallel lines, what can we say about the proportion split? Okay, so I want you to take 30 seconds, go and read the side splitter theorem.
So like a mid-segment, how is it like dividing the sides?
So the mid-segment divides it in half, or like, it's the mid-segment comes from our midpoint, so it's literally the halfway point. So now what we have, it's not the halfway point, but maybe the third
But
point.
they're
Or something like that.
still the same, these two are the same, these are the same.
It's not that these are the same, but the ratio is going to be the same. Which means when I compare the values, it's not that the values themselves are the same, but the comparison simplifies onto the same fraction.
I thought you meant like,
Okay. All right, so our side splitter theorem here. Again, what we have is we're within a triangle, and a line is parallel to one of our sides. So we're given this set of parallel lines here. What it does is it divides those sides proportionally. So these sides here that have been cut by that parallel line, are divided proportionally. And remember, proportional means same ratio. Same ratio. So again, last class we said you would have to compare your small triangle on top to the big triangle. Well, now we know that when the lines are parallel, we can go ahead and set up a proportion. So what we have is AB compared to BC is equal to DE compared to CD. So we have this proportion is true. Now notice I went in the same order. AB to BC, so bottom to top, equals DE to CD, bottom to top. Our properties of proportion says that I can flip this upside down, in which case I would have BC to AB, so top to bottom, and then top to bottom again. Properties of proportion says I can also switch my diagonal. Let me go ahead and do that one real quick. I'll write it out for you. So AB to DE equals BC to CD. So when I flip my diagonal, I'm basically just going AB to DE, so left to right, left to right. Because our properties of proportions holds true, it doesn't matter which order you go in, just as long as you're consistent with that order. So if I go left to right, don't then do right to left. Go left to right, left to right. So when we have these parallel lines, it cuts it proportionally, so that ratio, when we compare the values, is the same. It's not that our side lengths are the same, but that the ratios are the same. So go ahead and take a look at your classwork. I want to take a look at number 2 here. And I believe this is a 4 there, isn't it? So I've got 4, 16, 8. Alright, so here it says determine whether the given information implies that line QS is parallel to line AT. Take it back. Go back to your notes real quick. Sorry, maybe get to this. Okay, so our side splitter theorem says if the lines are parallel, we know those side pieces are proportional. The converse, right? Think back to conditional, inverse, converse, contrapositive. What does the converse do to our statement? Good, it flips it. So our converse then says, all right, if I start off knowing it's proportional, then that means the lines are parallel. So original side splitter, if the lines are parallel, I can say those pieces are proportional. The converse says if I have the pieces are proportional, then I can say the lines are parallel. Okay. So concept, parallel lines, proportional pieces, vice versa. So now we take a look at our classwork. When it says determine if we have information to imply that the lines are parallel, then that means in order for the lines to be parallel, I need to have those pieces are proportional. So we're going to go ahead and check our setup. And again, always label what it is that you're comparing here. So I'm just going to go QP to ST, or 4 to 2, left to right. So QP to ST. And we're going to compare to see, is that the same, put a little question mark over top, as QR to RS. So again, I went left to right, left to right. All right, let's go and fill in our values. QP is 4 to 2. Is that the same as 16 to 8? What does 4 over 2 reduce down to?
2 over 1.
Good. What does 16 over 8 reduce down to? 2 over 1. Woohoo! Yes. Q, S, parallel, AT. Since, I don't know we guys have this here. Since the pieces are proportional. Proportional. So that is our converse of side splitter theorem. Side splitter theorem. Now, if this were on a quiz or test, you don't have to say since the pieces are proportional. You can just say by converse of side splitter theorem. And since you just learned what that is, I'm going to kind of write down what that means for us. Okay. So again, side splitter theorem. When I have those lines are parallel, I can say pieces are proportional. Converse, if I have pieces are proportional, then the lines are parallel. Now, something you've got to be careful with is this can only be used for those pieces. Notice it does not involve the actual parallel lines. So go ahead and just put a note on your notes here. can only be used for the pieces. Can only be used for the pieces, not the parallel lines. And the reasoning there is that my pieces are only a portion of the entire triangle, whereas when I look at my parallel lines, that is the actual full side length there of the entire triangle. So if you try to compare pieces with the entire side length, the ratio is not going to be the same, because the ratio of those pieces is not necessarily the same as the ratio of the side lengths. So side splitter is only for those pieces. Whatever got broken up into pieces, that's what you can use it for. If I have to go back to solving for the parallel sides, then you're just going to go back to what we were doing last class. Compare your small triangle to the big triangle. Again, if you're ever unsure, just go back to comparing small. Okay, let's go and take a look at number 1. So again, in order for them to be parallel, we need the pieces to be proportional. And again, you can go in whichever order. Only choose as long as you maintain that order. So I'm going to go 34 to 35, 15 to 16. So I'm checking TS to PQ. Is that the same ratio as SR, QR? Okay, so I'm doing TS to PQ, SR to QR. All right, and then filling my values, 34 to 35. Is that the same thing as 15 to 16? Can I reduce 34 and 35? Nope. So definitely not the same. So tell me if it's parallel. QS is not parallel to PT. Since the pieces are not proportional. Pieces are not proportional. So again, pieces proportional, lines parallel, vice versa. All right, do we have any questions on 1 or 2? Okay. So let's go and take a look at another number 2, because I don't know where 3 went. It says find the value of the variable, show your work. So here they don't tell us if these triangles are similar, and they're not asking us to prove parallel. They gave us that they're parallel here. Okay. So we have parallel. That means I can use side splitter. I have parallel. I can use side splitter. So we're just going to go and set up our proportion. Now again, with side splitter, you're using just the pieces. So I have a piece of 20 and a piece of 12. That's awesome. I have a piece of C. But here 24 is referring to the whole thing. I don't want the whole thing. I want just the pieces. So how much would this piece here be? Good. 24 minus C. The whole thing is 24. Subtract away C. You're left with that piece there. So when we set up our proportion here, again, it's up to you. If you want to go left to right, top to bottom, bottom top, right to left, right to left. Whichever way you so desire, you'll get the same answer. I'm going to go ahead and say 24 minus C to 20 equals C to 12. So I went 24 minus C to 20 equals C to 12. And how do we solve these kinds of problems? Cross multiply. Always look to see if you can reduce first, but it doesn't look like I can, so let's go and cross multiply. So I have 12 times 24 minus C equals 20 times C. Now at this point you can go ahead and distribute your 12 or divide by 12. Let's see.
Distribute.
Alright, Cam's going to distribute. 24 times 12. You can thank Cam for that one.
Yeah, that's what we have to do on the test.
Yeah, so we'll do it by hand right here. No biggie. 4 times 2 is 8. And 4 times 1 is 4. 0. 2 times 2 is 4. 4 times 1 is 2. So 288. Okay. 288 minus 12C equals 20C. So add the 12, get 32C, then divide by 32. So let's see.
Why don't you throw you?
Right, added over. That is still the number one mistake that I see across the board, is that instead of adding 12 to c to both sides, you guys add or you subtract it. Or some of you will even do this, you'll actually write it out, but then still subtract it. I'm not sure what else to tell you other than to stop doing that. Just be careful. If you find that you're making that mistake where you subtract from both sides, maybe you need to take that extra step to actually write plus 12c plus 12c. And then just make sure you're actually doing what you said to do there. Okay, so let's divide by 32. Let's see, they're both even, so I can at least break it down in half. So we get 16. What's half of 288? 144. Awesome. Let's see. 144 is divisible by 12, so it must be divisible by 4. I mean, you can do it in half again, but I think we'll divide by 4. You want to half it? Okay, Cam said half it. We're going to do what Cam says.
72.
8 and 72. 72 divided by 8?
It's half it.
Come on.
Come on, it's half it.
What's 72 divided by 8?
36 over 4.
6.
What do we get? 9. 72 divided by 8 is 5.
Look, I want half.
I want half again.
Yeah, you can. Yeah,
Oh, thank you.
Solomon gets it. He's tripped out.
Just to be sure.
Just to be sure. Okay. Thank you, Sabrina. C is 9. Alright, so let the big number scare you.
I love the X.
Yeah, them big numbers are scary.
Well, don't let them scare you. Just divide by
Especially
2.
on a test when one of the numbers
Yeah.
is 1,000.
Yeah, exactly. I was like,
Mm.
what? Like, what's 60 times 64? Like,
Or you can work smarter, not harder, but we'll talk about that later.
nah, like, it's just.
Well, I don't know how to work smarter, so.
That's why I'm trying to teach you how to work smarter. Okay, I want you guys to go and try number 4. Again, same basic setup here. It's up to you how you set it up. Just make sure you follow the same order.
Does Henry look like a Henry or a Henry?
Like there's a second E, like HENERY.
You look a Henry, honestly. I can't remember. Henry.
So then work on number 4.
Alright. So. Henry, you done? Henry.
Once you get your answer, go and compare with your shoulder partner what you got.
Huh?
Shut up.
Oh yeah, Henry. Henry.
Say that one more time.
Henry. Hey, I thought you were gonna do something.
Damn. Did you do number 4?
Yeah.
Did you check with Zoe or Patrick?
I'm just
You got
smart
3.
guy.
Ah, I got 3 as well.
Smart guy. You even have to show work if you automatically know what it is.
You should always at least show the setup.
It's
Henry, don't
5,
question me.
18 over 5 divided, it equals 3. And you need, or, whoa.
Show your setup.
5.
Okay. Again, since there's multiple ways we can set this up, can I just have one volunteer tell me what their setup was? Yes, Henry.
Henry.
Do A over 9 equals 5 over 15.
Why would you do that? Henry?
So A over 9 equals 5 over 15. Perfect. And what do we get for A?
3.
Do you agree? Awesome.
Then that's it.
And again, I recommend working smarter, not harder. Reduce this first when you're able to, because it makes it so your numbers are smaller and easier to work with. Okay. So basic side splitter theorem, set up your proportion from your pieces and have I. Let's take a look at the ones below it, our corollaries. Alright, so corollary to side splitter theorem. So this is basically, it's not just a triangle with a set of parallel lines, but now what we have is 3 or more parallel lines. Okay, so we still have transversals. If you think about the side splitter, we have 2 parallel lines and basically 2 transversals there. So we're basically just going to take that scenario and extend it out. What if I throw on another parallel line and extend out my transversals? So that's what our corollary is talking about. So if 3 or more parallel lines intersect 2 transversals, so just this picture here, then the segments intercepted on the transversals are proportional. So again, we have proportional That means same ratio. This is really saying the same idea. My pieces are proportional. So my first thing here that says JK to KL equals ON to NM. So I went top to bottom, top to bottom. Or if we go, take a look at our next piece here, JK to ON equals KL to NM, which equals the whole thing, JL to OM. Now, we don't need 3 pieces. We only need 2 for a proportion. But it's just saying, hey, if you decide to, notice for the second part here, JK to ON, I went left to right, left to right, left to right. You can do that with the pieces or with the whole thing there. This first one, I went top to bottom, top to bottom. Okay, so again, it's up to you how you set up your order. Totally up to you. Just make sure you are consistent with that order. Now, this other corollary, again, is kind of a follow-up thought. We, once again, have 3 or more parallel lines. So it's saying for here, what if these are parallel? So let's go ahead and just mark in that they're parallel. And we still have our transversals here. But this is a specific case where our parallel lines are drawn in such a way, and our transversals are drawn in such a way, that it cuts off congruent segments. So what it's saying here is, okay, well, what if my lines are parallel, and on top of that, we know that GH and HJ are the same. Okay. So this is a specific case of the corollary before. When that happens, then I can know any transversal I draw through here will also create congruent pieces. So I can know then that when I draw this transversal, that I'm going to have these are congruent. I can draw another transversal through there.
How do we know that? How do we know that this?
Because what it is if you think of our ratio, or sorry, our corollary up here, it says that the ratios are the same. So if I go this compared to that, it's like saying, so like 1 to 1. If I compare this to this, it simplifies on the same ratio. Or if I go from here to here, like let's throw in some numbers. That might make it a little easier. I say this is 5. Let's just say that this is
7.
Sounds good. Okay. So according to my corollary up here, I can say 5 to 7, 5 to 7, the same. According to my corollary, I could go 5 to 5, 7 to 7. That would reduce down to 1 over 1, 1 over 1. So the ratio is the same. So what they're basically saying is, if the ratio is in such a way that these are congruent, then that's going to be the same ratio every time. So every transversal is also going to cut congruent like that. So if I go ahead and draw another transversal through here, these would also be congruent. So any transversal that goes through is congruent. We don't use this one very often, and honestly, if you forget this, but you remember the one before, you'll be fine. You just have to do a little bit of extra work. This is kind of like a shortcut for this specific case. So when you have the specific case that these are exactly the same, then any transversal through it will have congruent segments. So it's a specific case of the one above it. Okay. So again, side splitter pieces are proportional. Our corollary side splitter is saying the pieces are proportional. It's just that we have more than 2 parallel lines.
So the top one is saying JK is proportional to ON.
JK over KL is proportional to ON over NN, meaning they have the same ratio. So when I compare JK to KL, so top to bottom, that's the same fraction as top to bottom.
Okay, not the same wording.
Not the same length, but same fraction. Or I could go left to right, same fraction. So let's go take a look at our classwork again. Let's do number 6. I changed my mind. Let's do number 5.
Number 5.
Because it's dealing with just the pieces, then we'll take a look at 6 first. Alright, so again, when we have parallel lines, that corollary to side splitter says I can match my pieces. X to 8, 15 to 20. Or X to 15, 8 to 20. Or 20 to 8, 15 to X. Or 20 to 15, 8 to X. Totally up to you. Just maintain that same order. So I'm going to go X to 8. So bottom top equals 15 to 20.
Pieces.
Now again, I recommend working smarter, not harder. Reduce 15 over 20. What does that reduce down to?
Yeah. No, you're wrong, so.
So now you can cross multiply and get 4x equals 24. I'm just going to go ahead and multiply by 8 on both sides because I only need to get rid of my 8. So I'm going to multiply by 8 on both sides. And then I have 24 divided by 4, which is 6. Or you can reduce 8 and 4, so you have 3 times 2, which is still 6. Yeah. So side splitter theorem, so this is our corollary to side splitter. Side splitter is specifically when I have a triangle with the parallel lines. This corollary is when I have parallel lines outside a triangle. Now, technically, if I extend this out here, then I can apply side splitter with those. But like, this is not technically a triangle here. So I'm not using side splitter, but the corollary, which the corollary basically just says, we can extend out what side splitter says with multiple parallel lines. So that's a good distinction to make, because if it asks you to justify which one to use, side splitter has to make the triangle. Here, if you look, the pieces that I used were not the triangle. But if we look above, the pieces here that I used make up that triangle. See that difference there? It's the same concept in how we set it up and solve it, but side splitter specifically for triangles. Corollary says, all right, well, we can extend this out when it's not triangles, because essentially I could make this pointed together and then apply a triangle. Okay, number 6. Once again, we have piece 8, piece 12, piece Z, but they gave us the whole thing is 25. So what would I call this piece here?
25 minus 2.
Wonderful, thank you, Gabe. 25 minus Z. And then you can again set up your proportion and solve from there. So I want you guys to go ahead, set up your proportion and solve. Again, you can have different orders, just as long as you're consistent with your work. What are you going to be dividing by?
What is 6 times
What's 6 quarters give you? $1.50. Whenever I have 25s, I think in terms of quarters.
It's 150.
Okay, so we did get Z is 15. Who would like to volunteer what they did for their setup?
I got you.
All right, Cam.
25 minus Z.
25 minus Z over 8.
Yeah, and then 1 over 6.
Which is
1 over 6. Oh, no. 0 over 6. No, 0 over 6.
Z over 12.
Oh. Yeah, alright, my bad.
Good. So 25 minus Z over 8 equals Z over 12. Good. And again, you could have gone 8 to 12, 25 minus Z to Z, either way. But we should get an answer of Z equals 50. So in this particular problem, they did give us this whole length here. So again, we can go piece to piece, piece to piece. But if you want to use that whole length of 25, you can. So what would be, this is the whole length of those two pieces. So it would be the whole length here. 20. So if you wanted to use the 25, you could. What we would do is 25, 20, so top to bottom, equals, and then do a top to bottom again and Z to 12. And so, you could do the same thing there.
The Z's look like 2s. That's why I said 6. Because the Z, I thought the Z was a 2 when I wrote it down. No, I got 1 6.
Give a little line there to help you out. Okay, so again, doesn't matter which order as long as you're consistent with it. All right, let's go ahead and flip over our notes. We'll go back to our notes here. Now this theorem here, this is our triangle mid-segment theorem. You can go ahead and write that in. It's triangle mid-segment theorem. Triangle mid-segment theorem. And again, we've already learned this from a previous unit. This simply says that when we have the mid-segment, which is this line that connects the midpoints, is our mid-segment. The theorem tells us two things. One, it is parallel to that third side, and two, it is half the length of that third side. Now, the reason why this is true is from our side splitter. We can know it's parallel because, again, that ratio is going to be the same. 1 dash to 2 1 dashes would be 1 2 1 2. So we know it's parallel. And then, again, the ratio is 1 to 2 1 2 1 2. So, nothing new there, just a reminder. But again, if you forget that, you can just go back to what we were doing and set up your ratios. All right, so now say look at triangle angle bisector here. So this one's different. We're not dealing with parallel lines here. Instead of what we have is our angle bisector. So when an angle bisector is drawn in a triangle, it's going to hit the other side. And from 2 units ago, we said that does not necessarily hit at the midpoint. It might, but most of the time it does not. So what it does tell us is it divides the opposite side into 2 segments that are proportional to the other sides of the triangle. So again, same ratio. Same ratio. So when we have this angle bisector,
Can we borrow Natalia?
she is not here today. So when we draw on our angle bisector, what we have here is Fi to IH is equal to FG to HG. Now, let's take a look at properties of proportions, how we can switch this up. Let's go ahead and just change our diagonal here. This properties of proportion says I can change my diagonal. Fi to FG equals IH to HG. So the first way we basically did split segment to split segment, like left to right, left to right. So if I switch my diagonal, then we're saying Fi to FG, so bottom to side, equals IH to HG, bottom to side. So again, it's another situation where the order doesn't matter as long as you are consistent with your order. So I can go left to right, or bottom to side, either way. Questions with that one? Alright, so if you go on the back side of your classwork. Number 7, we have angle bisector theorem. And again, it's up to you how you go about setting this up. I'm going to go 21 to 33 equals 17.5 to cube. So 21 to 33, 17.5 to cube. Okay, notice it's the side, or it's the split segment and the side it's connected to. I don't want to do 21 and cube because they have nothing in common. One's the split segment, one's a completely different side. Okay, again, you can cross multiply. We talked about how when we have decimals, sometimes it's advantageous to multiply by 10 to get rid of that decimal. Because it's a half, we could also just multiply by 2. So I'm going to multiply by 2 over 2 on this side here. Again, think of ways to make the numbers easier for you to work with. On the left side, can I reduce anything over here? Yeah, what does 21 over 33 reduce to? Good, 7 over 11. Okay, so we have then is 7 over 11. What's 2 times 17.5? What's 2 times 17? There you go, 34, and then another one, 35. Okay, and then let's go ahead and cross multiply here. So I have 14 cubed equals 11 times 35. I'm not going to multiply that out just yet. Alright.
Oh,
Just because the number's gonna get really big, and I'm hoping I can reduce something with my 14. So I'm not gonna multiply 11 times 35 out just yet, because I'm gonna have to divide anyway. And then I'm gonna go and divide by 14. Alright. Is there any, can I reduce 11 and 14 or reduce 35 and 14? What can I reduce here?
14.
14 with what?
7.
Yeah, 7 goes into both 35 and 14, so that would leave us 2 on the bottom. What's 35 divided by 7? 5. So we have in Q is 55 over 2.
How do we do that?
So instead of multiplying 11 times 35 and then trying to divide that by 14, I'm just looking at my factors. I have 11 and 35 on top and 14 on the bottom, so I'm looking to see if I can reduce something. 7 goes into both 35 and 14. So 35 over 14 reduces down to 5 halves, divide both by 7. And then it's smaller numbers, easier to work with there. But because I think it's good for us to, I learned last year that not everyone knows the pattern for multiplying by 11, so I want to double check that. Now, you guys probably know 11 times any single digit, like what's 11 times 2? 11 times 4? 11 times 8? But once we get into our double digits, I learned last year, not everyone knew that pattern. What's 11? So this is just off to the side here. You don't have to actually write it out if you don't want to. What's 11 times 10? 110. 11 times 11? Anyone know what 11 times 12 is?
132.
132. So check out this pattern here. Taking a look at the number I multiplied by, 1 plus 0 is 1. So here's 1, 0, and 1 between. 11, put those on the end. What's 1 plus 1? 2, that's your middle number. 12, put those on the end. 1 plus 2 is 3, that's your middle number. So I can go 11 times 17, and I can know it's going to be 187. Did you guys know that?
Yeah.
That's so
How do you, what?
So I'm multiplying 11 times 17. So I basically take 17, split it apart, and the middle number is just the sum of those.
Oh,
So let's go like 11 times 15.
oh, that's pretty neat and smart.
That's pretty neat. Okay. All right. So anyway, your answer is 55 over 10. So again, it's the same idea for all of today. You set up your proportion. Doesn't matter what order, as long as you're consistent.
You know the 9 trick
You know what, how
with
much?
your fingers?
Yes.
Do it.
What do you want? 9 times what?
7.
1, 2, 3, 4, 5, 6, 7. 63. But also 2, 6 plus 3 is 9. All of the factors, the numbers themselves add to 9. Make 9 times 6, what is that? And 5 plus 4 is 9. 9 times 9? 81. 8 plus 3 is 9.
That's kind of crazy.
That's cool. Okay, do we have questions with this?
Yo, it's honestly not that hard. It's just what this is from 1 to 9.
Wait, does not everyone know the thing?
I don't know. I think Henry does. Henry.
Oh, like legit, you don't know it? Okay,
You never will.
I've never heard of
guys, I don't know what kind of elementary you're
James will taught us well.
Okay, so this works for your multiples of 9. So say you want 9 times 4. You count from the left, 1, 2, 3, 4, put down your 4th finger. There's 3s and 6, so 36 is your answer.
We learned that in 2nd grade. I don't know.
9 times 7, put down your 7th finger, so 6, 3, 63.
Keisha, we learned that in 2nd grade. Keisha was in my class in 2nd grade.
Well, apparently Cam was paying attention. Yeah.
Yeah. I was paying attention to this. Who'd you have in 2nd grade? Who? It's hard. Who's that? 2nd grade? Yeah. Who's in
That makes sense, because it's like 100 and then you take away the 1. I like that. Okay, I want you guys to go ahead and try 8. Let's just do 8 and then we're gonna go back to this. So I want you guys to go and try number 8. Oh, no, wait, I take it back. I want to do number 8 with you. Because
Thank you, Miss Margaret.
what's the difference between number 8 and our side splitters we were doing on the front side? Is it a 1 color?
It's not on the side, it's inside the picture.
Good. We have one set is the side that was split, but our other set is not the split sides. Side splitter. It has to be the sides that are split. So I cannot apply side splitter here. If I don't have those sides split, like the numbers, the split sides, I can't use side splitter. I have to go back to my original. Compare your small triangle to the big triangle. Compared to our big triangle. So in my small triangle, I have 21 and 15. My big triangle, was that an F? I have an F, and then what's this entire side here?
21.
21. So again, if it's not both, if the sides aren't both split, you can't use side splitter. You've got to go back to just original small compared to big. Okay, so now when we set this up, actually I should have first asked this. We have to know that it's similar. Are those triangles similar? The big and the small? Why? They only gave us one angle there.
They share that.
Good, they also share this. So we have they are similar by angle similarity postulate. And beyond that, if these are congruent, what types of angles are they compared to these lines? What type of special angles are they? Corresponding. So we technically could say these lines are parallel by converse of corresponding, and then you could use corresponding there. But either way, they are truly similar by angle similarity postulate. So now when we set up our proportion, I'm going to go F to 21. I did not write.
Miss Margaret.
Yeah.
Can we not do side splitter because we don't know that they're parallel or sublet?
Well, we can show that they're parallel because
So we could
corresponding.
do side splitter.
If they gave us these
Oh, yeah,
values
right.
here, then yeah, you can do side splitter. Okay, so I'm going to go F to 21 equals 21 to 14. And again, I recommend work smarter, not harder. Simplify when you can. What does 21 over 15 reduce down to? 7 over 5. Again, you could cross multiply. I just simply want to get rid of my 21 though, so I'm going to multiply by 21. If you prefer cross multiplying, that's fine. You're just doing one additional step. Ugh, I can't reduce 5 and 21. What's 7 times 21? Let's see, 7 times 20 gives us 140. 7 times 1 is 7, so 147 over 5. Okay, so again, this is one you've got to be careful with. Put a big star, be careful. Because after we learn side splitter, then I find some of my students try to do the side splitter all the time. And you can only use side splitter when you are using these split sides. One of my sides is not split, can't use side splitter. Okay, so back to our notes now. Our very last thing. So we've got this beautiful diagram here. Some parallel lines, and they even threw an angle bisector. So you're going to fill in the blank of what's the remaining side for this proportion, and it says justify your answer. So that means you're going to say either by side splitter theorem, corollary side splitter theorem, converse of side splitter theorem, triangle angle bisector theorem. So the theorems that we've learned here, that's going to be your justification. And again, just a reminder that side splitter makes a triangle. Okay? So if I am using this piece, this piece, this piece, this piece, those together do not make a triangle. It's not the side splitter, it's going to be your corollary side splitter. But if I use those pieces, oh look, those do make up the triangle side splitter. Okay? So side splitter is when we actually truly have that triangle there. So go ahead and fill out those remaining segment measures and which theorem you're using for it. Feel free to work with your shoulder partner on this. And again, we'll come back together and go over it. What'd you get?
KS.
Which theorem is it though?
Angle.
Yeah, triangle angle bisector. Very good.
Uh,
You got it.
Please put it.
Okay,
That's fair.
let's see how we did with this. So the first one, we should have gotten KS. 26, we should have had SQ. 27 was SP. 28, that's a J. Yeah, that's a J. SQ is not a segment. Thank you. 28 was KP. 29 KM. 30 PF. All right, now let's take a look at the justification. So for number 25, we had triangle angle bisector theorem. That theorem up here again.
What?
Did we have that for any
Yes,
other ones?
yeah, I think we
Which
had
one?
28.
28 was also triangle
Yo.
angle bisector theorem.
Tomorrow from nice with this.
Any others that had triangle angle bisector theorem?
No, no,
Yeah.
21.
29 was also triangle angle bisector theorem. Pretty much anytime you're using the sides and bottoms of that angle being bisector. All right, what was 26? Side splitter theorem. Good. Side splitter theorem. And the other side splitters? 30 was also side splitter. And then what was number 27? Corollary to side splitter. Good. Corollary
So what was 26?
to side splitter. Okay, which ones of these do we have questions on? Whether it's the the actual answer or the theorem. Any of them? Sure. Speaking off for everyone, please. Which one? 27. Okay, so when we take a look at 27, we have QL to PM equals SQ to JP. So I went bottom to top, bottom to top. And because I'm using just the pieces and those together do not make up that triangle, then I have the corollary to side splitter. Others that we have questions on? Okay, so let's go ahead and take a look at that very last classwork problem. Remember, look for opportunities to work smarter, not harder, when we're dealing with decimals. We talked about how we can multiply by 10 to get rid of decimals. We got some how we can multiply by 2. They gave us multiple pieces here, so we have quite a few options as to how we can set this up. What do you guys want to do?
7.5 and 6.
Okay, 7.5 to 6.
And 1.25 to 12.
Good. I like that setup because you're going ahead and using the smaller numbers to start off with. All right. Now, properties of proportions. Again, we could switch our diagonal here. We can go ahead and cross multiply. I'm going to switch my diagonal because I know I can reduce 6 and 12 a lot nicer. So I'm going to say 7.5 over 1.25 equals 6 over 12. We can also flip the whole thing upside down. I personally prefer to do that, but we'll just leave it for now. What does 6 over 12 reduce down to? 1/2. So now when I cross multiply, it's actually not too bad if I have decimals, because what's 7.5 times 2? 15. And 1.25g times 1 is just 1.25g. Now, I personally don't like to divide by decimal, but I can convert this into a fraction pretty easily. What's 1.25 as a fraction?
1 1/4.
1 1/4, so 5/4. Okay. So now I'm just going to multiply by the reciprocal to get rid of that. 5 plus 4.
Could you just multiply 4 to 5, 15?
Yeah, you can multiply by 4 on both sides and then divide by 5. And then So again, you can multiply that and get 60 divided by 5, or I'm just going to go and reduce. What is 5 and 15 reduced down to? Yeah, so I've got 1 on the bottom, 3 up here. So 4 times 3 is left on top, 1 at the bottom, so 12. So again, look for ways to work smart with your decimals. Just multiply by 10 the number. Alright, what's your homework? Worksheet 4. Nothing crazy, just a normal one-page paragraph worksheet. Oh my goodness. Make sure you... Well, I'm going to do it this way. Here's a stack. Here's a stack. Grab and go.